Quantum physics has a reputation for being complex and hard to grasp. Richard Feynman, a Nobel Prize winner, famously said, "If you think you understand quantum physics, you don't understand quantum physics." While this quote can be daunting, it's somewhat misleading. We actually understand quantum physics very well. It's one of the most successful scientific theories and underpins technologies like computers, digital cameras, LED screens, lasers, and nuclear power plants. Quantum physics deals with the smallest entities in the universe, such as molecules, atoms, and subatomic particles. At these scales, things behave differently than in our everyday world. Instead of viewing electrons as tiny particles, quantum mechanics describes them as waves, known as wave functions. These wave functions aren't physical waves like water waves. They are abstract mathematical descriptions used to determine properties like position or momentum. To find an electron's position, we use the amplitude of the wave function squared, resulting in a probability distribution. When measured, an electron appears as a point-like particle within this distribution. In quantum physics, we deal with probabilities, not certainties. This idea marked a departure from the deterministic universe of classical physics. The wave function model accurately predicts subatomic behavior, but no one has observed a quantum wave directly. We only see particles upon measurement, which collapses the wave function. How this collapse happens is unknown, a gap called the measurement problem, which Feynman alluded to in his famous quote. Quantum physics also raises the question of how to picture an electron. It seems like a wave until measured, at which point it behaves as a particle, illustrating wave-particle duality. This is famously demonstrated in the double-slit experiment. If you fire particles at a wall with two slits, you'd expect two bands. But when scaled down to electrons, they create an interference pattern of stripes, typical of waves. The electron wave goes through both slits, overlapping and forming areas of high and low probabilities on the back wall. This experiment shows that electrons act like waves, leading to the question, what happens to the wave when measured? It appears to change from a wave to a localized particle, but quantum mechanics doesn't explain this process. This mystery extends to all particles, making the double-slit experiment pivotal in understanding the universe. To address these questions, physicists have proposed various interpretations of quantum mechanics. The wave function also helps explain other quantum phenomena. One concept is superposition, where a wave can describe a particle existing in two places at once. This happens because the wave is a combination, or superposition, of other waves. Another is entanglement, where particles become linked, sharing a single wave function that describes them both, even when separated by vast distances. Measuring one instantly influences the other, a concept Einstein found troubling because it seemed to imply faster-than-light communication, though it doesn't transmit usable information. Quantum tunneling allows particles to pass through barriers. A wave function decays when encountering a barrier, but still has a chance of appearing on the other side, enabling particles to tunnel through. Quantum tunneling is crucial for nuclear fusion in the Sun, which powers life on Earth. The Heisenberg uncertainty principle is another fundamental aspect of quantum physics. It states that one cannot know both the position and momentum of a particle with absolute precision. Position is given by the wave function's amplitude, while momentum is tied to its wavelength. A perfect sine wave has a defined momentum but no specific position, while a well-defined position means uncertain momentum. This principle is not due to measurement limitations, but is inherent to nature. The term quantum refers to discrete packets of energy. This concept first appeared in atomic spectra, where atoms emit light at specific energies because electron waves in an atom are quantized to certain wavelengths. When an electron shifts from a higher energy state to a lower one, it emits a photon of light with a specific energy, resulting in the discrete lines seen in atomic spectra. To sum up, quantum physics describes particles with wave functions, which appear as particles when measured. This leads to wave-particle duality and the measurement problem. These wave functions explain phenomena such as superposition, entanglement, quantum tunneling, the uncertainty principle, and energy quantization. Understanding these basics provides a solid grasp of quantum physics despite its complex reputation. For a deeper dive, check out Quantum Physics for Beginners by James Carter at Barnes & Noble. It's an accessible introduction to these fascinating concepts.